Hello, let's begin one more lecture session on multivariate calculus integration. In the last lecture session, we have talked about Gauss's divergence theorem, which relates surface integrals with volume integrals. Today's lecture session, we will see another very important theorem, Stokes theorem. And we will see that Stokes theorem will relate surface integrals with line integrals. So let us now see the statement of the theorem. So let S be a piecewise smooth oriented surface in space and let the boundary be a piecewise smooth simple closed curve denoted by C. Also, let F be a continuous vector function with the components Pxyz, Qxyz, Rxyz having continuous first partial derivatives in some domain in the space which contains S. Then Stokes theorem states that the line integral f dot dr along the closed contour C is equal to the surface integral del cross f or curl f dot n ds over the surface S. Here, this notation of course tells us that the line integral is taken over a closed curve. However, S is an open surface bounded by the closed curve C. And N is the unit normal vector to S, and this is drawn in the sense in which a right-handed screw would advance when rotated in the sense of description of C. So let us see some important points about Stokes theorem. The first one, we have already observed that Stokes theorem relates line integrals of vector fields to surface integrals of vector fields. Next, let us see the Stokes theorem in coordinate form. So the form is like this, that the line integral p dx plus q dy r dz, this is equal to the surface integral del r del y minus del q del z dy dz plus del p del z minus del r del x dz dx plus del q del x minus del p del y dx dy over the surface S. Now, as we have seen that F is having the components PQR and dr is of course having components dx, dy, dz. So F dot dr reduces to P dx plus Q dy plus R dz. Similarly, if we look into the components of the vector curl F, we can easily prove that the right hand side in coordinate form will take this form. Note one more thing. In case we are in the plane xy that is given by z equal to 0, the left hand side will reduce to the line integral p dx plus q dy and the right hand side will just reduce to the surface integral del q del x minus del p del y dx dy, as both these expressions will be 0. And now, since we are on the xy plane, so of course the surface integral is nothing but a double integral. And we can easily remember this expression, line integral p dx plus q dy is equal to the double integral del q del x minus del p del y dx dy is nothing but the statement of the Green's theorem. So we may now state that Stokes theorem reduces to Green's theorem in the plane. Let us now look into problems involving Stokes theorem. So the first one, show that the line integral yz dx plus xz dy plus xy dz is 0 along any closed contour C. Let us apply Stokes theorem to prove this result. So as we would like to apply Stokes theorem, that means we would convert this line integral into a surface integral. And we know that in Stokes theorem, the surface integral involves curl F. So we need to find that now. And what is F over here? We can observe easily that the components of F are here, yz, xz and xy. So as per our notation, we can say that P is equal to yz, Q is equal to xz and R is equal to xy. So let us now calculate curl F. So curl F is given by this 3 by 3 determinant. We all know it's ijk del del x, del del y, del del z, and PQR in the third row. So this gives us I multiplied with del r del y minus del q del z plus j multiplied with del p del z minus del r del x plus k multiplied with del q del x minus del p del y. And as we now substitute these values of p, q, r, we easily see that this reduces to nothing but a zero vector. As here, let us check once. Del r del y is going to be x, and again del q del z is also x. So this component along the x direction becomes 0. Similarly, the component along y direction is also 0, and that along the z direction is also 0. So therefore, finally, we can see clearly that curl f or del cross f, this is a 0 vector. And now we remember the statement of the Stokes theorem that the line integral is equal to the surface integral curl f dot in ds. So as this curl f is a 0 vector, we see that this final answer to the line integral also becomes 0. So we have proved that along any closed contour, this line integral will have a value 0. Let us move on to another problem where we will now verify the Stokes theorem. So the question is, verify Stokes theorem for f equal to 2x minus yi minus yz squared j minus y squared zk, where a is the upper half surface of the sphere x squared plus y squared plus z squared equal to 1 and c is its boundary. So let us first draw the figure. So this is like this. Here we see S, the upper half surface of the sphere, x squared plus y squared plus z squared equal to 1, and C is the boundary of this hemisphere, which is of course a circle of radius 1 on the xy plane. So C will actually be represented as x squared plus y squared equal to 1, z equal to 0. Now, as we need to verify the Stokes theorem, so we would like to calculate both the line integral as well as the surface integral. So let's first calculate the line integral along this circle C. So f dot dr along the circle C will be now given like this, as f is having the components 2x minus y minus yz squared minus y squared z, and dr will of course have the components dx, dy, dz. So this is our expression now for f dot dr. And since for the circle z equal to 0, so therefore this term minus yz squared dy will vanish, and also minus y squared z dz, this term will also go away. So we are only left with the line integral 2x minus y dx along this circle C. And now to evaluate this line integral, let us use parametric coordinates x equal to cos t, y equal to sin t. So this 2x minus y dx now becomes 2 cos t minus sin t, and dx is minus sin t dt. And of course for the circle, t varies from 0 to 2 pi. So as we simplify this expression, this term, first term will become minus 2 cos t sin t, so minus sin 2t, and the second term will be plus sin squared t, so we have written that as 1 minus cos 2t by 2. So this we can easily integrate, and as we put the limits, we will see that the answer will come as pi. Let us now proceed to evaluate the surface integral, and therefore first we need to calculate the term del cross f or curl f. So curl f, as per the formula we have, this is ijk del del x del del y del del z, and here we have the components of the function f. So 2x minus y minus yz square minus y square z. So let us now calculate this. So with I, we will have del del y of minus y square z, which gives us minus 2yz, minus del del z of minus 2yz square. So we will get plus 2yz. For j, we see that we get del del z of this expression, which is 0. minus del del x of this expression minus y square z. So this is again 0. So the component in the y direction is 0. And with k, what do we get? This is del del x of minus yz square, which is again 0, minus del del y of 2x minus y. So this will give you a plus 1. So finally, we can see from here the value of this line integral is the unit vector k. So let us now proceed to evaluate the surface integral. What is the surface integral we need to calculate? We know that is curl f dot n ds. Now see that we project this surface S on the xy plane in order to evaluate this surface integral. So we remember the formula. We have seen that if we do such a projection, then ds is given by the formula dx dy divided by n dot k. And now please remember that our del cross f we have just now evaluated to be k. So this becomes the surface integral k dot n dx dy divided by n dot k. And see that of course this integral now is on the surface S1, which is the surface of the plane on the xy plane bounded by the circle C. So this cancels of course, and therefore we'll be just left with the double integral dx dy over S1. We know very well that the double integral dx dy gives the area of the region of integration. And the region of integration here is of course a circular region bounded by the circle of radius 1. So of course this is a very well known result that the area of this circle will be pi r square, where r is 1. So this is nothing but pi. So therefore we have seen that both the line integral and the surface integral had the same value pi, and hence we can say that the Stokes theorem has been verified. With this, we will close today's session, and this also completes this module of multivariate integration. So thank you very much for your patient hearing.